Welcome to EPG Pathshala and the third module on sequential clinical trials. Thus far, we have generally concentrated on the case of continuous outcomes. The calculations of sequential plans have been derived for this case when we have a normally distributed variable with known variance by Armitage in his 1969 paper, and based on this, it has generally been possible to adapt this to calculate the corresponding plans in the case where we are using a group sequential design. This has been done by Pocock and has been discussed in the previous module. However, as we know that in many situations the appropriate outcome is not continuous in nature, and a very common alternative is to have a binary outcome. So for example, we could be looking at a binary variable which takes the value 1 or 0 depending upon whether the patient is cured or survives or experiences some particular life event. In the introductory lecture, we briefly considered this situation and have seen that 3 alternative metrics have been discussed in the paper by Whitehead, one based on treatment differences, one based on the log odds ratio, and the third based on the difference of a function of the treatment. In general, Whitehead's conclusion is that while the function can be chosen optimally so as to guarantee certain statistical properties, notably that of Brownian motion, the more interpretable choice is that of the treatment difference. Thus, we shall concentrate on the difference in the proportion of success between the two treatments, say A and B. We shall look at the difference PA minus PB. We shall derive the sampling design, and we shall see that, as before, it is based on iterative numerical calculation. We shall also derive the average sample number, and finally we shall take a quick look at the R package GS design, which we shall visit in more detail in the following module. Learning objectives for this module: we shall first define the binomial trial in the case where our outcome is binary, or the number of successes on the standard treatment and the comparison group. We shall define sequential designs for this case. We shall look at the iterative calculations which are necessary to derive these sequential designs. And finally, we shall take a quick glimpse at the GS design package in R for implementing group sequential designs. Our approach in this paper will be based on the paper by Elfring and Schultz entitled Group Sequential Designs for Clinical Trials, which appeared in Biometrics in 1973. Closed sequential procedures for binomial sequences have been presented by several authors: Bross in 1953, Armitage in 1960, Spicer 1962, Olling in 1966, and Choi in 1968, and Breslow in 1970. So the general procedure in these cases has been to consider a pair of patients in which one member of each pair is assigned randomly to one of 2 treatments. Tied pairs are discarded, and the situation is reduced to the framework of a binomial sequence by eliminating the tied pairs. Then testing of the pairs will continue until the binomial sequence reaches one of the decision points. So these designs are closed in terms of the untied pairs rather than the total number of pairs. And there is some uncertainty to the investigator who is planning such a clinical trial. In many cases, it is more convenient to deal with more than one pair at a time. That is, we do not assume that an analysis is conducted after every pair is enrolled in the trial, but rather we specify a maximum number of interim analyses which will be performed before the trial concludes. In this case, it makes sense to opt for the group sequential design for clinical trials. We are assuming here that P1 and P2 denote probabilities of success with treatment 1 T1 and treatment 2 T2 respectively. As the subjects enter the study, they are formed into pairs, with each pair being treated with one member being assigned to T1 and the other to T2. The number of pairs per step may be variable. There is no extra information associated with the pairing. Now consider only whether success or failure results from the treatment. Each pair is scored and the data looks as is given on this slide. The probability and the score for each outcome are as given here. So in the first case, we have the first subject on T1 observing a success, the second on T2 observing a failure, and we know that the probability of this event is P1 into 1 minus P2. Similarly, the probability of 2 successes is given by P1, P2. The probability of 2 failures is given by 1 minus P1 into 1 minus P2, and the probability of failure on T1 and success on T2 is given by 1 minus P1 into P2. We thus have a sequence of random variables x1, x2, etc. such that x1 takes the value plus 1 with probability P1 into 1 minus P2, which we denote by Q1. Probability xi takes the value 0 with probability P1, P2 plus 1 minus P1 into 1 minus P2 equal to Q2. And probability xi equal to minus 1 takes the value minus 1 with probability 1 minus P1 into P2, which we denote by Q3. We thus have a trivariate distribution. Let S be the sum of the random variables for any given state G with n new pairs. The probability that S new is equal to n for given values P1 and P2 is then determined by the sum of trinomial terms which have been given on this slide. So summation m equal to nu plus mod nu by 2 to n nu plus nu by 2, n nu factorial by m factorial, n nu minus 2m plus nu factorial, m minus nu factorial, q1 to the power m, q2 to the power n nu minus 2m plus s into q3 to the power m minus nu. A sequential plan will then proceed as is given on this slide. In the various columns of this table, we have denoted the stage, whether we reject H0 for H2, whether we accept the boundaries for H0, reject H0 for H1, and the number of pairs which we look at each stage. Note that after the gth stage is completed, the sequential procedure specifies that if summation Si is less than equal to Rs, the testing will terminate and H0 is rejected for H2. If it is greater than equal to Rs dash, then testing terminates and H0 is rejected for H1. When G is less than equal to J, and if summation Si lies between Rg and R dash G, testing will continue into the G plus first stage. When G is greater than J and summation Si lies between A G and A dash G, the testing will terminate as H0 is accepted. If the sum lies between Rs and Ag or A dash G and Rg dashed, the testing will continue into the stage G plus 1. Iterative calculations then are specified by C of M P1 P2 equal to summation I nu to W C G minus 1 I P1 P2 into BQ M minus I P1 P2, where V is the maximum of Rs minus 1 plus 1 and M minus Ns, and W is the minimum of Rs minus 1 dash minus 1 M plus Ns. Thus, the probability that S1 plus S2 and so on is equal to M at the gth stage is the probability that it is equal to I times the probability that the remainder is equal to M minus I summed over all eligible values of I and M minus I. The probability of accepting H0 at state G, where G is greater than J plus 1, is given by LG P1 P2 equal to summation of CG M P1 P2 from AG to AG star. The probability of rejecting H0 for H2 at state G is given by RG double dash P1 P2 equal to summation from Rg minus 1 minus Nu plus 1 to Rg Cg M of P1 P2. Similarly, the probability of rejecting H0 for H1 at state G is given by Rg dash P1 P2 equal to summation M equal to Rg dash to Rg dash minus 1 plus Mg minus 1 Cg M P1 P2. And thus, the total probability of accepting H0 is given by L of P1 P2 equal to summation G equal to J plus 1 to K Lg P1 P2. Similarly, for H1 and H2. The average sample number is given by ASN equal to summation G equal to 1 to K N nu into L nu P1 P2 plus R nu dash P1 P2 plus Rg double dash P1 P2. And similarly, from this expression we can also obtain the variance of the average sample number. So, the general decision rules for sequential design for the one-sided hypothesis H0 P1 equal to P2 against the alternative P1 less than P2 are as given here. In stage 1, we accept H0 or reject H0 for H1, and the final column denotes the number of pairs observed at each stage. The OC can also be obtained in a similar manner. Plan construction. Note that to construct the plan it is necessary to specify some parameters such as the standardized difference, and we may not have much knowledge about them initially. To get around this, we can perform sensitivity analysis. The procedures which have been used here are generally quite flexible and can be adapted to include any kind of testing regions, truncation rules, etc. The authors recommend that we study the behavior of the OC and the ASN over a range of treatment differences, especially in the situation where we might not have much prior idea about the range of treatment differences to expect. And finally, for more detail, you are referred to the papers by Mainland in 1967 and 68 and Colton in 1968. Mainland and Colton discuss the advantages and limitations of sequential procedures in clinical trials, and of course the major advantage is that a superior treatment is identified with fewer experimental subjects than is usually possible in an experiment with a fixed sample size. A quick glimpse at the R package GS design, which we shall revisit in the final module on sequential clinical trials. This slide gives you the typical syntax of the function GS design. So you can see that there are many arguments. K is the number of analysis planned, including the interim and the final. The test type, which could be one-sided, two-sided, symmetric or asymmetric. Alpha, the type 1 error. Beta, the type 2 error. A star, which is normally not specified, but if test type is 5 or 6, that is if we are using two-sided asymmetric tests, then A star will specify the total probability of crossing a lower bound at all analysis combined. Delta, which is the effect size for the parameter theta and can be set to a standardized effect size. N.fix, which is the sample size for a fixed design with no interim analysis and is used to find the maximum group sequential sample size. Timing, which is a relative timing of interim analysis. Timing, an option which sets the relative timing of the interim analysis. SFU, which is a spending function or a binary type. SFL, which specifies the spending function for the lower boundary. SFU par defaults to -4 and is an O'Brien-Fleming-like conservative bound. SFL par, which is the default bound set to -2 and defaults to the Huangshi-Decamy spending function. The tolerance R is an integer value controlling the grid for numerical integration. N.I is used for resetting the bounds when the timing of analysis change. Maximum.I plan is used for resetting bounds when the timing of the analysis changes from the initial design. N-fix-serve is used if a time to event variable is used. Endpoint is an optional character string that should represent the type of endpoint used for the study. Delta 1 and delta naught may be used to store information about the parameter scale, and delta naught is the null hypothesis parameter value on the natural parameter scale. In the next module, we shall consider these options, the output and implementation of the GS design using an example. In this module, we looked at group sequential designs for the case when the outcome is the proportion of successes or failures. Our choice of the parameter of interest is the difference between the proportion of success on the experimental treatment and the new treatment. We have considered a setting here where the patients are enrolled in pairs. The pairs do not really have any meaning other than the randomization is done so that as the patients accrue, the pairs are formed and each member of the pair is randomly allocated, one to the treatment and the other to the reference. We look at the difference in the outcome and define a trivariate random distribution. Subsequently, we use numerical procedures to find the corresponding sequential plan, its ASN and its OC. Finally, we looked at the R package GS design and its many options, and we shall go back and consider this package in more detail in the final module on sequential clinical trials. Thank you.